we've been circling around this idea of equilibrium, and I think we all have sort of an intuitive sense of what equilibrium is, but nonetheless, I looked it up in the dictionary. And, well, looked it up in the dictionary. What do? You just type in equilibrium and Google spits you a definition. Anyway, I did that, and I learned that a definition of equilibrium, certainly not that of the OED, is a state in which opposing forces or influences are balanced. That is, things are calm. Well, maybe not calm, but certainly stable, reasonably stable. And I have here our trusty dusty pendulum. It's in relative equilibrium. It's not as much in equilibrium as it was a few minutes ago because I bumped it and moved it. But anyway, you can see it's just hanging there. It's not doing anything. Well, it's hanging there in equilibrium. And we'll remember that when we were talking about the pendulum a while ago, we said that in an ideal world where there is particularly no friction, the pendulum will have an attractor that looks like this. And it will just keep, where this is the displacement, this bit, and the velocity, how fast it's going. We'll make that into a D rather than a gamma. Right, and in that perfect world, it's a vacuum. There's probably a little bit of, there's got to be some gravity, but there's no friction, there's no loss. It just does that, and that's actually an equilibrium. But in the real world, where there is another force, so friction is a force, the top does this, right, in the attractor space. Probably a little bit longer than that. That's a lot of friction for a pendulum like that. But we end up with no displacement. It's hanging at zero, and it's not going anywhere. It's not a velocity. So it's in equilibrium, and that equilibrium state is here. And the forces that are balanced are the gravity, the pull of gravity down, and against the strength of the string, and other forces having to do with it going back and forth have been dissipated into the entropy of the atmosphere. Well, the atmosphere, entropy of the universe. Entropy always increases, and as a result, pendulums in our world come to rest as that one has. So that's a static equilibrium. It's just hanging there. There's no other forces holding it. Well, there's gravity, but there's no motion there at the moment. So let's see. We talked about a pendulum. And then I set you a homework assignment focused on a top, which I have a number of. I have some toys on my desk that contribute to my procrastination, among other things. And one of the things about this wobbly top, this one wouldn't spin nearly as nicely as the one in the video, is that it spins around, and it spins around an axis here. And what you didn't see is that, in fact, it spins in a dish that has some curvature, not nearly that exaggerated. And in the middle of the video, as I pointed out, it kind of just does that. It's kind of boring for a lot of the time. At the beginning of the video, this axis wobbles around a bit more. And then at the end of the video, it wobbles around a lot. And eventually the top ends up, I've never drawn it on the side, but the top ends up something like this on the desk. Boo. All right, so that's obviously an equilibrium. That's an equilibrium. But this middle bit is also an equilibrium, and it's a dynamic equilibrium. I talked about the restoring force. The restoring force comes from the fact that you have this spinning bit right there. So the top being stable in its spin is dynamic equilibrium. Dynamic equilibrium. And of course, then the top lying on my desk, usually outside of the little spinny tray, is of course static equilibrium. All right, so that's two kinds of equilibrium: static and dynamic. Now, another example of equilibrium that we've looked at is the predator-prey, the ideal Lotka-Volterra predator-prey model. Let's see. In that one, we have some predators and we have some prey. And I've done that wrong, but it doesn't matter, really. Because what I'm really interested in is the attractor, predator, prey. And we had an attractor that kind of was egg-shaped, like that in general. Sometimes it's an egg shape going this way. Sometimes it goes, depending on the details. But for any given set of parameters, this is constant, and this goes around and around and around. So again, this is a dynamic equilibrium. The forces of the relationship between predator and prey are in balance, and we're ignoring influences in the ideal model. We're ignoring influences of climate or hunting or floods, and of course, in the real world, that's not true. But in the model world, we have this dynamic equilibrium where the predators keep the number of prey down, and they do so at such a rate that the prey go low. Oh gosh, this is terrible, isn't it? Need a little bit less. Need to be a little bit more closer. Anyway, they keep each other in check, essentially. The predators by eating the prey, and the prey by reducing in numbers as the predators eat them. So again, another dynamic equilibrium. All right, and then finally, some of you have looked at by now, others of you will look at soon, there's the homeostatic case of Daisy World, where, and I don't have a diagram for this one actually, where the black and the white daisies the area occupied by the black and the white daisies changes over time, depending on the incoming luminosity, and in a way that's governed by this growth parameter beta. Again, so that's a homeostatic it's a self-correcting system, much like our bodies, like I mentioned yesterday. So those are what do we have? Three main types of equilibrium. I'm sure there's others that we haven't touched on and that I haven't thought of. And then, of course, I'm going to leave you here with a little. Well, of course, I am going to leave you with a little question. It's just a thought experiment. It's not an assignment or anything. But we should be wondering: is Earth in equilibrium? Right. Uh, the answer probably is it depends. All right. Later.